When I have any linear transformation from a vector space to itself, even if that vector space isn't Rn, we can still ask the question, what things are left unchanged? Remember, transformation that goes from a vector space to itself is called an operator. If I have any vector in my vector space, as long as it isn't the zero vector, then I can figure out if it's going to be an eigenvector for this transformation, even if this transformation has nothing to do with little arrows and nothing to do with Rn. And my definition is exactly the same setup. We have an eigenvector if there exists some real number lambda, so that t of x is lambda x, and lambda is the corresponding eigenvalue. So I have an eigenvalue and an eigenvector. But this applies to vector spaces that have nothing to do with Rn. An example. Our signal space. I'm going to use a periodic signal. So this is cosine k pi over 2. K is an integer. Write that down here. K is an integer. So what does this signal look like? What's cosine of 0? It was supposed to be a chime. Cosine of 0, 1. Cosine of pi over 2. Cosine of pi. Cosine of 3 pi over 2. Cosine of 4 pi over 2. This is going to repeat. That's what this signal looks like. I'm going to create a transformation on the set of signals. This is our shift operator, isn't it? But we're shifting right, not the left, by 2 and not by 1. Sorry, we're shifting left, not right, because we're adding 2, so we're going this way. We're shifting the whole group over by 2. Are there signals that don't change, or that change by only a number? Let's look at our periodic signal. This one, this is our signal Sk. What happens when I do this transformation to this signal? Everything moves 2 spots to the left, yes? Hey, wait a minute. The 0 is going to end up on the 0. The negative 1 is going to end up on the 1. 0 is going to end up on 0. 1 is going to, wait a second. The result looks like that. Compare that to the original signal. What's the difference?
It looks the same, but the negative ones are swapped with the ones, and the ones are swapped with negative ones. And
Which
zeros are all still zero.
But that's the same as if I took the entire signal and multiplied by 1. This is an eigenvector. And the corresponding eigenvalue is -1. Because this is -1 times the original signal. T of my vector is number times my vector. This is an eigensignal. I don't want to call it an eigenvector. It's not a vector. Well, yeah, sure it is. It's a member of a vector space. It's a vector. And the corresponding eigenvalue is -1. As a matter of fact, there are lots of different eigenvectors for this transformation. I could figure out, I could multiply this by any scalar, right? If I put any number in front of it, that number would still, they'd still flip places, right? Instead of 1 minus 1, 1 minus 1, it could be 3 minus 3, 3 minus, as long as I switch the places, it would be like multiplying by -1. Matter of fact, I wrote this signal in terms of a cosine, didn't I? SK was cosine k pi over 2, where k was an integer. And we said we were shifting by 2, right? Shifting by 2 would mean to add 2 to this index. My transformation of SK was SK plus 2. Well, according to my formula, that would be cosine of k plus 2 pi over 2. Trig was a long damn time ago. But that looks like I'm adding 2 things together. I'm adding k pi over 2 and 2 pi over 2. Don't we have a formula for that? The sum of two, a cosine of a sum? Trig identities was a damn long time ago. When's the last time you took a trig course? Exactly. When's the last time you tutored trig? Those of you that are in the tutoring center? Oh, crap. It's been a while. All right, wait a minute. There was a formula for this. I remember, because I'm teaching trig this semester, that's cosine of the first thing times cosine of the second thing minus sine of the first thing, sine of the second thing. What's cosine of pi? -1. What's sine of pi? If that's multiplied by 0, that whole piece goes away. So look, if the original signal is cosine of k pi over 2, the shifted signal is minus cosine of k pi over 2. There's another way to show that this is an eigenvector whose eigenvalue is -1. I didn't even have to write out the whole damn signal if I remember my trig identities. That's always a question mark as to whether or not I remember my trig identities. But visually, if I were to graph what this signal looks like, here in figure 1, here's a signal in blue, and in this case, we only shift over, we shift how many spots? 2 over, right? So the blue dot here becomes the blue dot here. The blue dot here becomes this dot here. This dot, they move over, right? And see how it's changed the signal? And if we compare where it is, we can figure out whether this signal is an eigenvector or not. Pictures drive me a little nuts, especially for signal spaces. But the idea that eigenvectors don't have to be arrows in 3 dimensions and really can be in any vector space at all actually helps me. But I found eigenvectors using matrices. There was no matrix here. I don't like that. I like this calculation we were doing for the past few days. This wasn't difficult. Finding the lambdas, then finding the vectors that went with each one by finding a null space, those were nice. I would really like to do this with matrices, but in order to do that, I need to somehow figure out how to make a matrix for any linear transformation from a vector space to itself. Let me start with an assumption. We start with the assumption that my dimension of my vector space is finite. Well, then I know that I have to have a basis, right? If I know my dimension, then there has to be a basis with that many vectors in it. I don't know what that basis is, but there has to be at least one basis with exactly that many things. Then everything in the vector space V can be written in terms of its coordinates in that basis. We have a function that takes any vector to its coordinates relative to that particular basis. Wait a minute. This is in V, right? What's this in? What vector space does the coordinate vector live in? Rn. Because each of those entries is a number. How many the first vector? How many the second vector? How many? Aha! I can do this for any vector, right? Any vector in V, I can find its coordinates, and that'll be something in Rn. So what if I took that? Where does that live? That lives in my vector space V, because T goes from V to V. So when I do T of something, that's in my vector space V. But that means it's got coordinates. Holy crap, wait a second. Hang on a second. By using coordinates, I turn my arbitrary vector space V into some sort of representation in Rn. I'm going to rearrange this picture a little. I have my vector space V. I have my transformation T that goes to V. So something over here becomes something over here, right? I have the idea of using coordinates. Coordinates goes to Rn. Coordinates goes to Rn. I don't have a name for it. So I need a name for this map that takes something and gives me coordinates. Most of the time, I think of this as projecting from V to Rn. So we tend to call this a projection map. Projection starts with a P. I'm going to call this map pi 1. Actually, I'll just call it pi because there's only one of them. The projection from V to Rn. We talked about this before. Because we have a basis, that map is 1-to-1. Because we have a basis, that map is onto. Which means that that map is invertible. If I know the coordinates, I can tell you what the vector is. So I could take this particular picture and say, instead of trying to figure out how to go from here to here, I'm going to figure out how to go from here to here. And then I'm going to go down, over, and up. This is a transformation from Rn to Rn. Every transformation Rn to Rn that is linear has a matrix. Which means I can build the matrix for this by going the long way around this picture. And it's pi times whatever this matrix is here on the bottom, let's call it M, times pi inverse. That's a similarity, isn't it? It means those two things have the same characteristic polynomial. Eigenvalues. Okay, wait a minute. This vector here, xb, xb, that's a set of numbers, R1, R2, all the way up to Rn. Because that's an n-dimensional vector. T of x. Up here. T of x is in terms of my basis. That would be T of R1 times the first vector, R2 times the second vector, all the way up to Rn times the last vector in my basis, right? That's what having x being written with those coordinates means. But T is a linear transformation. What can I do with that big ugly addition and multiplication in there? I'm all the way back in chapter 1. What can I do with this? Not yet. But a transformation is linear if for two conditions. Remember our sheared sheep? Chapter 1, section 8. Transformation is linear if the transformation of a sum is the sum of the transformations, and I can take a multiple from the inside to the outside. Which means I can take that giant adding and scalar multiplying and separate it to separate multiplications and additions. We called this the superposition principle. Chapter 1, section 8. It was a long time ago, I understand. But that means that this can now be written R1 T of B1 plus R2 T of B2 all the way up to Rn T of Bn. What are the coordinates for this in the basis B? Well, I would need to know these vectors in terms of the basis B, right? So if I want the coordinates for T of x, I really need the coordinates for each of these pieces. Chain, number times column, number times column, number times column. This is a matrix multiplication. And the matrix I am using has as its columns the basis representations of the image vectors. This matrix right here, this giant list of columns, this matrix is exactly the matrix I called M up here. Holy crap! Every linear transformation on any vector space is a matrix transformation in some basis. Ready? Example time. Here is a vector space. I'm going from two-dimensional polynomials to one-dimensional polynomials. And here's my transformation. Oh, hang on. That should be a 2 there. Because I was going from the vector space to itself, right? God, I need to go from the vector space to itself. What is a basis for the space P2? That's the dimension would be 3, so I need 3 things. What are the 3 vectors that make up the standard basis for a set of polynomials of degree 2 or less? This is like the exam question, but on the exam question it was degree 5 or less. Now I'm only going up to degree 2. What is the basis? Almost. Not just the numbers 0, 1, and 2.
0, x 1, x 2.
They're not x
squared, x squared, I mean.
0, x to the 0, x to the 1, and x to the second. But x to the 0 is just 1. And that means that I can think of these 3 things as polynomials. That's 1 plus no x's plus no x squareds. Right? So the first vector in my basis has coordinates 1, 0, 0. What is t of 1? It is 0, which is 0 plus 0 x's plus 0 x squared. So the transformation of B1 has coordinates 0, 0, 0. I'm going to keep that. Because that's what I need right up here. That's the first column of the matrix M for this transformation. What's the middle column? Well, let's look at the second vector. F2 of x is x. That's 0 plus 1x plus 0x squared. What's t of x? A0, A1, A2. What's this do?
Would it be AX plus 2A 2 X
Oh.
squared?
What are those numbers in this case? A1 is 1. A2 is 0. So I would get 1 plus 2 times 0 times x. Which is just 1. Right? Write that in our basis. T of the second vector has coordinates 0, 1, 0. No. 1, 0, 0. 1, 1. No x's. No x squared. 1, 0, 0. I got to write it the right damn way. Sorry. Let's do the same thing for x squared. X squared is 0 plus 0x plus 1x squared. What is t of that?
Plus 2 times 1 squared.
0 plus 2 times 1, x. Which is just 2x, right? But I'll write it as 0 plus 0x, plus 2x. I can write 0 plus 2x plus 0x squared. What's the column coordinate vector for that? The coordinate vector, in terms of the basis, is, what's the column here? 0, 2, 0. The matrix M looks like this. Now, what the hell does this do? I want you to make up for me a quadratic polynomial. Give me some polynomial. F of x equals.
X squared plus 7x plus 2.
Because I wrote all the other ones in increasing order, I just turned yours into increasing order of powers, right? What are the coordinates for that? In the same basis we've been using, what are the coordinates for this?
2, 7, 4.
Right. Multiply that times our matrix M. This is not a particularly difficult matrix multiplication this time, because there's only one non-zero number in the first two rows. The bottom row is all zeros. So 0 plus 7 plus 0. 0 plus 0 plus 8. 0 plus 0 plus 0. This is the coordinates for my transformed polynomial, which means that my transformed polynomial, undo the coordinate, take the inverse of the coordinate transform. Let's go back from this to polynomials. I did the transformation without ever going back and looking at A0 and A1 and 2 and whatever that crap formula was, right? I did this transformation by doing a matrix multiplication. I just took a derivative without ever doing any calculus. You sneaky son of a bitch. Isn't that the derivative there? Isn't that the derivative of this? You take f plus g prime, you take the derivative of each one. You take a number times f, you take the derivative. You leave the number alone, you take the derivative. That's a linear transformation. The linear transformation has a matrix. I just found a matrix, a derivative. Here's a question for you. What possible eigenvalues that matrix have? It's the only eigenvalue, right? That's a triangular matrix. So the diagonal entries, all the eigenvalues are 0, which means I could figure out what the eigenvectors were, right? I can do the eigenvalue-eigenvector calculation from that matrix. So now I can ask you the question, and it's going to sound like a calculus question. What functions get multiplied by a constant when you take their derivative? What polynomials? Because remember, I'm in the space of polynomials. 0i minus a equals 0. I do my reduced row echelon form, and I get this. Well, that tells me that the second constant is 0, the second entry, and the third entry, right? So C2 is 0 and C3 is 0, but C1 is anything. So the vector There's the eigenvector for the eigenvalue 0. Which means whenever you do this transformation to something that looks like 1, 0, 0 or a number 0, 0, you're going to get 0 times that vector. Let me go back and think in the universe of polynomials again. What kind of a polynomial is this? It's got no x's, it's got no x squareds. This is a constant. What's the derivative of a constant? 0 times that constant, isn't it? Derivatives have eigenvectors. Every linear transformation has eigenvectors, provided I can find the right basis to think about it in. Now, with that in mind, if I'm thinking of this just working in Rn, then I'm automatically working in a normal matrix, right? I don't have to do this matrix conversion crap. So I see my transformation as a matrix to start with. But if I'm working in other vector spaces, I don't see that. I see a description first, but I can still turn that into a matrix and then work with it. So what was we were doing on Wednesday? We were diagonalizing. And to find out that it was diagonalizable, I had to come up with enough eigenvectors. I had to come up with enough eigenvectors to make a basis. That was the very last theorem, the very last part of the very last theorem. I had enough eigenvectors in each eigenspace. I glomp them all together, and that's a basis. And we had this, right? P, A, the inverse. This diagonal matrix is exactly a new matrix representation for the transformation A. Only it's in terms of this basis made of eigenvectors. By changing my basis, I change my transformation from being some ugly matrix to a diagonal matrix. Theorem 8 says basically what I just worked out loud. If you know you can do a diagonalization, then there's a way to write this ugly transformation, the transformation given by A, T sub A. In terms of this particular basis, it behaves like diagonal matrix. Diagonal matrix is expansions and contractions, and maybe reflections, nothing else. You multiply by a number in this direction. You multiply by a negative number, so you have to reflect. And if the number is bigger than 1, you're making it bigger. And if the number is smaller than 1, you're making it smaller. And if the number is 0, squish, like grape. Every matrix transformation, when thought of in terms of its eigenvectors, looks like those matrix transformations we looked at in chapter 1. Expansions, contractions, reflections, that's it. Projections, which is a contraction by 0. As a matter of fact, I can even make this looser. I could say it doesn't have to be diagonal. It could be any two similar matrices. Then this matrix P is the way of rewriting a basis to make one transformation into the other. There are several figures that walk through the examples visually. Here, in example 4, page 300. Here's our transformation. When I actually create the eigenvalues and eigenvectors, I get these. So that means if I were to rewrite this transformation in this basis, now remember, this first vector is down at a 45-degree angle. The second vector is down further. So these are not at right angles to each other. They're at some funky looking angle to each other. But in terms of this basis, this multiplies in the 45-degree direction by 5. It multiplies in the other direction by 3. It's a dilation. It's just not equal. It's not like a pinch zoom. It's kind of skewed up. I would never have gotten that from here. Not ever. But what we've really done is used this sort of a diagram. I don't want to work between these two weird spaces. I want to work from R3 to R3 because it's easier. Matrices and real variables are much easier to work with. And that means that every that I can use as a vector space foundationally becomes, when it's finite, Rn. The infinite case, I don't know how to deal with an infinite matrix. We'll save that for a grad school class. Example 5 in this actually shows you one that isn't diagonalizable. It does the Jordan normal form that I mentioned on Wednesday. So if you want to see what that's about, look at example 5. I will see you all on Monday. Have a lovely weekend.